Okay, guys, I'm going to go ahead and get started. If you have a question, just open your mic. The computer is too far away from me to see a message if you send a message by text. So if you have a question, just open your mic, ask your question, close your mic, and we'll see how this is going to work out for us this time. So today I want to talk about analog and digital. It'd be good if you had the topic sheet out in front of you. You do want to take notes on this. Had I given you a quiz today, it would have been over the lecture from the intro lecture and mainly this one. So this is actually pretty important to understanding the PLC and what we're going to do for the rest of the class. So you do want to take good notes and get the topic sheet out. That might be handy. If you don't, it's not a big deal. Before I get started with that, though, I want to review two things that we talked about that's important from the last lecture. One of them was this device called a relay. And we described how a relay was constructed. Basically, there's two main parts to a relay. There's the electromagnet. This is the electromagnet coil. I have the whole circuit here, power source, and switch. Now, the switch is not necessarily part of the circuit, but for what I have on the board, you can see how this is going to work. If I close the switch, I have magnetism around the coil. If I open the switch, no magnetism. So I have a switch here with the spring, and that spring is forcing this switch up. So you can think of this right now as a normally open switch. We talked about normally open and normally closed. As a matter of fact, the way I have this now, this contact, when I do energize the relay and this contact closes, then this will be the normally open contact, because with no power on it, the contact is open. There's no reason why, if I wanted to, there's no reason why I couldn't take and put a second contact right here. And if I do that, I put the second contact right there. If I have no power on the relay, its normal state, this contact right here, that will be your normally closed contact. So we talked about last class, switches being normally open and normally closed. So I have a relay. We mentioned that the coil circuit has a high resistance, which means it has a low current. That's a good thing, because most devices that drive other devices, electrical devices, their output is a low voltage, low current. So you need something with a low current. So because the coil resistance here is so high, the current in this circuit is low, there's nothing stopping me from hooking this up to some device like a computer or some other kind of microcontroller to get the device to turn the relay on and off instead of having the manual switch here. Now, the other thing we talked about is the idea of this and or not logic. So we looked at switches that are hooked up in series. Say this is switch A and switch B. We call that AND logic. If I have some device hooked up over here and I want that device to turn on, so I had power on the left side and some device I want to switch on the right side, then the only way to get the device on is close switch A and switch B. So this is what we call AND logic. We looked at that. The other thing we looked at was OR logic, basically the same two switches, but now they're hooked up in parallel, and it's easy to see that if I hook it up this way, again, if I have power coming in on the left, some device on the right, I can close. If this is switch A and this is switch B, I can close either switch, or I can close both switches. Either one, either A or B or both A and B will give me an output over here to some device. We call this OR logic. And then I didn't give you a very good example last time, but we talked about normally closed and normally open push buttons. So if I have a push button, that's a normally open push button, but we also talked about a push button that's normally closed, and we use this to represent not logic. So if you didn't see the first video, you want to go back and definitely review that, because the rest of the semester, basically this stuff, just not with switches. So the idea here, though, is that instead of having manual switches that we have to actually physically open and close that require human interaction, we want some kind of device to control this for us because the object of the class is to automate things. So here's what we can do. What we'll do is, the relay has two parts to it. The coil, we're going to represent that coil like this. And we'll give it some kind of name. You can call it coil. I'm gonna represent it. I'm gonna call it CR. And so if you see that symbol, that's a coil. It's this. Now I did put a picture of an actual relay. If you didn't have a chance to go look at the course website, look at the course website. One of the first documents there, you'll see a relay, and it actually shows the structure and the parts of the relay. And then at the bottom, there's an electrical diagram of a relay. So if you look at that electrical diagram, it's different than what I'm going to show you here. So here, we're going to, instead of drawing the coil like this, we're going to use this to represent the coil. And this CR stands for control relay. I got to give it some kind of name. Later, we're going to call that name an address. So I have the coil, and if that coil is energized, it'll pull the armature down to the normally open contact, and this switch will be closed. So I want to represent that normally open contact like this. So this represents a contact that's normally open. And the contact at the top, the normally closed contact, I'm going to represent that like this. It's a line through it. This is a normally closed contact. We'll use these symbols for the rest of the semester to represent relay coils and contacts. Never again will I draw it this way. Well, I shouldn't say never again. At the end of the semester, you'll see that again. But for now, we'll think about it like this. So the coil, a circle with some kind of name on it. I just named it CR for control relay. Two contacts. If I have a normally open, normally closed contact, I can represent normally open this way, normally closed this way. As kind of a side note, I can have more than one armature. Let's say you're looking down at this. You're above it looking down. And I can have maybe the relay coil is like this, or the contact is like this. And then I have the electromagnet moving this in and out of the plane of the board. There's no reason why I can't have multiple armatures in there with contacts on it. I can have relays in many shapes and sizes. But the point I want to make is this. What we can do, instead of using switches for and or not logic, we can actually do that with relay contacts. And the beauty of that is we can use a relay, we can use some other device to control the relay. Therefore, we can automate a system. We can have as I said before, we can have a computer, microprocessor, or some other device control our relay for us and basically control our and or not logic. But I want you to watch this diagram I'm going to draw. This is important. So I'll get rid of this, and what I'm going to do is use these symbols over here. If I wanted to, here's what I could do. Imagine I have two parallel wires. So I had these two wires like this. We'll call this L1 and L2. Line 1 and line 2. Now, in reality, I'm going to put a battery down at the bottom, but in reality, you won't have that. But this is just so you can see it and think about it. Suppose I have and I'm going to just draw it in. I'm going to dot it in since it's not really there. But imagine the battery right here, or some kind of power source. So I got my battery right there across there. What I can do is I can take and I can hook up. Let's say I'm gonna hook up this relay coil, but I want to be able to control it with a push button. So I'm going to do this. I'm going to take a wire and connect to L1, and I'm going to put a normally open push button right there. And then over here, I'm going to put that relay coil. And so right now, if you think about it, if I have L2 and L1 here and power between them, if I push this button down and close the contact, now current can flow through this circuit right here. Now, I want you to imagine current flowing from left to right. Anytime we look at this diagram, and I'll give this diagram a name in just a few seconds, we always think of current flowing from left to right. Sometimes you'll hear people talk about power flow. Power really doesn't flow. Power doesn't flow. Current flows. Voltage does not flow. Power does not flow. Current flows. But for this class, we'll talk about current flow, and sometimes you'll hear me say power flow. We'll let you get away with that. I push this button, current flows to the control relay coil, and what's going to happen is it's going to close this contact, the normally open contact, and it's going to open this contact. If I release it, it's going to open the normally open contact and close the normally closed contact. So what I can do below this is I can take, suppose I have this, and then maybe I have a lamp. So I got a lamp, and I got a normally open contact, but you don't know what relay belongs to. That's the purpose of that CR. We call it a name, but it's really an address. So I'm going to call this, for now, since I just have one, CR. If that relay had two contacts, I might call it CR1 and CR2, or CRA and CRB. Some kind of way you got to distinguish one from the other. But you can see how this is going to work now. If I push the button here, current always flows in these diagrams from left to right. It's going to energize the control relay coil. It's going to close this contact, which is going to turn that light bulb on. If I release the button, since that's normally, it has a spring in it, when I release it, it's going to come back up like a doorbell. That coil's going to release. That's going to open up, and the light bulb's going to go off. Now, this is a really simple diagram, but it's called a ladder diagram. Ladder. And the reason they call it a ladder diagram is because if we keep doing this, keep putting these lines across here, it starts to look like these look like the rungs of a ladder. So they call this a ladder diagram or a ladder circuit. Now here's where this gets interesting, because what I can do is I can have many control relays here. I can have many control relays, and what I can start to do is to wire those contacts together like this. I'll extend the circuit a little bit. What if I had a relay coil that controlled this contact and this contact? I'll call this contact A, this contact B, and over here, I could put a lamp, or I could put a motor, I could put something there, but what I want is any old device. So I'm going to just do this, put some parentheses there. So that can be whatever you want to be. This is some kind of output device. This is what we want to control. Now, on the ladder diagrams, your inputs or switches are always on the left, and the last thing in the ladder is the output device. So on that first rung, we have one input device, a normally open push button. The output device is the control relay coil. On this rung down here, we have a contact, even though it's controlled by that coil, that's actually an input device. And the output device, the thing we're controlling, is the lamp. Here, though, is interesting, because somewhere else in this ladder, I got a coil that controls contact A, and somewhere else I got a coil that controls contact B. And they're in series, so if you think about two switches in series, what is that? I have switch A and switch B in series. In order to get something over here to operate, both A and B have to be closed, so that's end logic. So maybe you got something out in the field, you got something out in the factory, you got a switch or some kind of sensor to close this contact. If this condition is true and this condition is true, then start a motor or do something. Or maybe I want to do it like this. I can have a contact here, and I can branch off another here, like that. And again, I have some kind of output device, lamp, motor, whatever you want it to be. But now these contacts are in parallel, switches in parallel, that's OR logic. And now I have a source where I can have either contact A or B closed, or both of them closed, and control whatever this is hooked to. And you can see as you start pairing these together, hooking ands and ORs up together, you can really control pretty complex processes. So this is the diagram. When I hook it up using logic with this, then this is called ladder logic. Ladder logic. And this is what the course is based on. Now I know you guys did a homework where you looked at the history of the PLC. For PLC, the PLC is a programmable logic controller. All it is a computer. All it is a computer. And if you remember, I believe I said during the first lecture, a computer is not necessarily your laptop or not just the PC that you bought that you have on your desk, a desktop. In reality, a computer is anything that contains a microprocessor. So your laptop contains a microprocessor, it's a computer. Your desktop contains a microprocessor, it's a computer. But so does your cell phone. Your cell phone is a computer, it has every device a computer has. A microwave, if it can store, if you can program it, you call the microwave, it's a computer. So a PLC is nothing more than a computer. It's a heavy-duty computer designed to work in the industrial environment. Now, before PLCs, when they wanted to have electrical circuits make decisions, this is what they would use. Back in, I don't know, the 50s, 60s or something like that, before my time. Ladder logic. And so you'd have switches that would open and close, and you can run a whole factory this way. And you can imagine the wiring, if I had, these are pretty simple things I'm doing here, pretty simple logic. But you can imagine if I'm actually putting it together like a car, and I have an assembly line, and I have a ladder controlling that, you'd have very, very complicated logic. And so back in those days, this was the way it was done, but it wasn't easy. And you had electricians to go in, and you had these big racks with all the relays switching back and forth and switches and all kinds of stuff. And it was a nightmare until the PLC came along. So we'll talk about the magic of the PLC and what that did for us. But in a nutshell, what it's done is replace all of this stuff right here, hardwired logic, with software. And we'll get to that later on. But I want to get to something else, because really this lecture is about analog and digital quantities. I want to talk about that in some detail. Now, if you think about this circuit right here, this ladder, there's something common about everything in that circuit, in that ladder. And what that thing is that's common is that no matter what I have here, the switch, the coil, the light bulb, no matter what, it's either in one state or another state. So what I mean is like that push button. That button is either open or closed. That relay coil is either energized or not energized. The lamp is either on or off. Anything I have in this diagram is this in either one state or another state. A motor could be running or not running. And when you have something that exists in one state or another state with no in between, that relates to what we call digital. Digital is I'll call it a school of electronics where, well, we'll put it like this. There's two sides to an electrical house. There's the analog side and there's the digital side. So analog means that we can get any value, we have an infinite number of values. But digital means that we use one value or another. And I want to spend some time talking about this. So let's get into that topic and take good notes on this. Analog and digital. Now you've heard these terms before. People usually apply them the wrong way. Well, I shouldn't say the wrong way. When lay people talk about analog and digital, they mean many things, but to scientists and engineers, we mean something very specific when we talk about analog and digital. And I should really say analog quantities. analog quantity. So analog means continuous. It means continuous. Now, when we talk about these quantities, now what do I mean by quantity? Well, whatever I mean by quantity, any physical quantity, we're going to turn that into an electrical signal. So here's what I'm saying. Some quantities that are analog might be temperature, time, pressure, speed or velocity, sound. I can keep going on and on and on. These physical quantities vary continuously. They don't jump from one value to another. So if I look at the temperature and I look out, I'll take a temperature measurement and it might be, let's say it's 68 degrees. It doesn't jump over to 69 degrees. It goes through an infinite number of values. It gets up to a higher temperature. So if I want to take any of these physical quantities and turn it into electrical voltage or current, I use a device called a transducer. If you had me for circuits, we actually talked about transducers. So let me put that on the board, a transducer. A transducer is any device that changes energy from one form to another. So for example, a speaker is a transducer. You put in electrical energy, you get out sound. A motor is a transducer. You put in electrical energy, the shaft spins, you get out mechanical energy. That's a transducer. Some transducers can go both ways. You can take a speaker and speak into it, you get out electricity. You can take a motor and spin the shaft, now it's a generator. So a transducer takes energy and changes it from one form to another. So what we do is we use transducers to take these physical quantities and turn them into a voltage. So what I have is one of these right here, one of those physical quantities go in, and I get some kind of proportional voltage out. Let's say voltage or current. So I get out a voltage or a current, and it's proportional to the input. So I can take a temperature. When you probably have a thermometer with this virus thing going on. You have an electric thermometer. The thing you put in your mouth is a thermal resistor or some kind of thermocouple. You take your temperature, it takes the temperature of your body and changes it to electrical signal. And there's a little chip, a little circuitry inside that changes that to a digital display, an output that you can read. It's a transducer. So if I were going to say, have a transducer that, let's do temperature, or it can really be anything. Let me draw a diagram for you. The point is, though, this physical quantity that you can think of, there's some kind of transducer that can change that into an electrical signal. An analog of something means a copy of something. Now, it turns out that most, if I want to say all, but I won't say all, almost all, probably all, very close to all physical quantities, anything in nature, basically is analog quantity. Most quantities in nature are analog. So let me go back to my example. It could be temperature or whatever. Say we had some kind of transducer. Actually, let me put this over here. So I have some kind of transducer. So maybe I have time on this axis. And if it could be temperature, it could be pressure, it could be whatever, I'm just going to put amplitude. The amplitude is just the amount of voltage or current produced by the transducer. So let's say whatever this transducer is doing, maybe you're measuring the temperature at regular intervals, or you're doing something at regular intervals, and you get a signal that looks like this. Maybe you start off right here, and you go up like that, and then it just goes on. This is an analog representation of whatever physical quantity we that we inputted into the transducer. This is an analog quantity because Never did you see me lift the marker off the board. This is a continuous line, a continuous drawing. So analog signal, the analog signal is continuous, it's not broken. So one way to think about or define analog is just the word continuous. I really want to talk about analog so you kind of compare it, or contrast it, I should say, to digital. Because digital is really a process to get to. What I want to do is take this analog signal and I want to digitize it. And this actually happens all the time. If you think about it, you might not know this, but by the end of the class you will. Any computer, that means your PC, your laptop, your cell phone, your microwave oven, anything with a microprocessor in a computer cannot or does not operate or understand analog. Computers only understand digital. You might have heard machine language, but basically it's digital. If I want to send anything into any kind of thing, any kind of device with a microprocessor, it cannot be analog. It's got to be digital. So right now you're looking at me on camera. The light is hitting my body, it's reflecting, going into the camera. That's analog. But when it gets into the computer, there's circuitry in there to change it over to digital. Because that microprocessor wouldn't know what to do with an analog signal. When you speak into your cell phone, you're talking to your cell phone. And when you take a picture, you make a movie with your cell phone, all that information going into that device is analog. But when it gets inside of the circuitry, the chips, the microprocessor, it doesn't know that it's changed over to digital. So how do we go from an analog quantity to a digital quantity? That's a process. And I want to show you that. Now this is simplified, but you'll understand it when I'm done. So this is my analog representation of this quantity that's changing whatever it is in nature. I want to digitize it. So I can maybe send it to a computer, send it out over the internet, do whatever. So what does it mean to digitize a signal? Well, what you do when you digitize a signal is you quantize it. And I want to show you what I mean by that. So this is the analog representation of it. I'm going to draw a graph on the below. You're going to think it's the digital representation, but it isn't. I'll explain that in a second. So we got time down here. So this is exactly, you guys are watching me right now on video. The light hitting my body going into that camera is analog. What I'm going to show you right now is exactly what this computer is doing and what your computer is doing, or cell phone or whatever, when you use it, if you input analog information. If I want to digitize this signal, if I want to change it to a digital signal, what I have to do is I'll sample it. I'll take samples at regular intervals. So interval is just a piece of time. So maybe I'll break this up into intervals like this, and I'm not going to draw all these lines all the way across. And the circuitry, that what it will do, you put one over here, like that. What the circuitry will do is it'll take samples of the signal at regular time intervals. So it might take a sample, let's say we start over here at 0. That line is really at 0. And then it'll take a sample right here. And then it'll take a sample right here. And then it'll take a sample right here. And then here. I'll take a sample here. You can see what I'm doing. I'm taking these samples at regular intervals. And so the actual graph, these red dots I'm drawing, the actual graph down here looks like this. I got one here, and then that one's about like right here, 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 like this. I don't know, you guys are, when I was coming up, we had things where you connect the dots. If you connected these dots, you'd have that analog signal back with you. So what happens is the circuitry actually goes in and samples the analog signal at regular intervals and produces this value right here, but it doesn't stop there. What happens next is that each one of these dots is given a numeric number or code. Now for right now, we'll think of a number and a code as the same thing, but they're really different. I'll explain that next week. But I got a numeric number or code. The only thing is the digits that I use to represent the code, the digits, can only be a 0 or a 1. So what I'm saying is this. This dot right here, I'm going to represent that value with this code, 0, 0, 0, 0. And that one right there, I'm going to represent that with 1, 1, 0, 0. And maybe that one is 1, 1, 1, 1. And this one might be 0, 1, 0. Every dot here is given a value using zeros and ones. And this is what we mean by digitizing, because each of these dots right here represents information. And now the information is represented, instead of some kind of quantity, it's represented as a code or a number with these zeros or ones. And we'll get to the significance of the zeros and ones in just a second. Now, if you're in the classroom when you're looking at this, this is about the time in the class where some student will raise their hand and say, well, hold on a second. Suppose this is sound, this signal, this analog signal I have. Suppose it's sound or whatever. Look at this right here. Look between at this and that. I'm going to put that off over on the side. Let me redraw that. I'm going to take just this part of the graph and blow it up. So I got these two red dots like this. And then I got the blue line going up kind of like this. And then it keeps going. All of that blue line in there is information. So if I digitize it, if I sample it and I represent this blue graph with these dots, what happened to all of this right here from that dot right there to that one? And everything in between, that's information. So what happens to that when I digitize it? And the answer is, you can see, it's gone. We threw it away. And you might think to yourself, well, that's a terrible thing, or is that a bad thing? We're actually throwing information away. This graph is nowhere as detailed as the blue one. Is that a bad thing? And the answer is, I don't know. It depends on what we're doing. It might be a bad thing, but let's say I want to get a better estimation of this signal right here, using this idea of taking a sample and putting a dot down there and assigning that dot a code with zeros and ones. And I want to, so I don't actually, I want to, when you deal with zeros and ones, we call that binary. Binary. I want to use the term binary. I can say it. I've been trying not to say it without defining it. So zeros and ones is binary. We'll get into binary pretty deeply. Binary. Zeros and ones, binary. And a binary digit, is a 0 or a 1. A binary digit is a 0 or 1. What they do is they take the B from here and the IT from digit, and they call it a bit, a BIT. So a 0 or a 1, 0 and 1 is binary, but a 0 is a bit and a 1, those are bits. So if you heard the term bit before, that's where that word came from. So we go in here and we sample the signal. And by sample, we got some circuitry that looks at the analog signal at a certain time, at a regular time. It takes a sample of it, puts a dot there, and gives that a binary code, gives that a binary value, zeros and ones. And it keeps doing that to reproduce the signal. And I'm asking, well, look at this. You just threw all the information away. I got a dot here, a dot. What about the information in between? Is that good or bad? It might be bad. Let's say it is bad, but you want to get a better approximation of this. What would you do? Well, what you can do is, now this is called sampling. I can sample this. I've sampled it here and got that dot. I sampled it here and got this dot. I can increase the sampling rate. Instead of looking at it during these number of intervals, maybe I do this. I look at it in shorter intervals so that I have more dots now. In other words, now I can put some dots in between there. So still kind of bad because I have information that's kind of thrown away, but that's better than just the two. There's more information in between here. So there's a term I want to use. It's called resolution. You've actually heard this before. I don't know if you know what it means or not. but you've heard the term resolution. Resolution refers to digital quantities. So resolution is how many of these points. A point is either there or not there. And digital is either one thing or another. So here I have a point, 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 here I have a point. If I represent, let me actually show you this way. I'm going to make a line. This is a good example. So here's a line. But if I digitize that line, what I would do is take a sample and another sample. All the information in between this point and this point is thrown away. If I want a better representation of that line, I just sample at a higher rate. So I sample at a higher rate, which means I'm going to represent that now with more dots. Maybe I got this number of dots. Is that good enough? I don't know. I don't know what we're doing. But if it's not good enough, what I can do is I can sample more and more points, and you get a point to where I can have these dots so close together. This is a much higher resolution than this, and this is higher than this. This is way higher than this. This is analog, that doesn't count. But the digital representation, these dots are not what's digital. Make sure you understand that. Each one of these dots is represented by zeros and ones. What's the purpose of that? Well, let me get to that in a second. Make sure you understand the idea of resolution. If you got a flat screen TV, or you guys know I don't have a cell phone, so I was looking at a video on YouTube on my PC, which costs, I don't know, $1,500. The monitor was hellaciously expensive. I'm looking at this video the other day. My 23-year-old nephew comes and pulls out his cell phone. He brings up the same video, and it looked like I was looking at it in HD. The damn cell phone, the resolution was so much better. So if you have a flat panel TV, you know the way they work is they have little LEDs or basically little lights that light up to make the picture. And the number of, well, I said the picture, but each one, if I'm talking video, audio stuff or video stuff, I have a matrix of dots that make up your TV screen, microscopic. You can't see them with your eye. They're really close. So I might have a dot right there that can either be on or off, or it can go through a variety of colors depending on what digital code you put in. But that would be called, if I'm talking TV, that would be called a pixel. And what they do on a TV screen or a printer or anything we're talking about digital, they'll look at the number of maybe pixels in an inch. And the more pixels you have per inch, the higher the resolution. Here's another example. I don't know if you guys know what a Polaroid is, but when I was a little boy, there was a camera, a Polaroid camera. You can snap a picture of it, and the film will come out and you do like this, it'll develop right in front of your eyes. It'll just develop. That's an analog photograph. Let's say I have a picture that I take with a Polaroid camera. And I can't really excuse my artwork, but I want to have a picture here. And then my picture, this is the Polaroid. I got, let's say I got a person. That's my person. And I got a house. Person standing next to a house. So this is my analog photo. Analog, because if you take it with a Polaroid camera and look at the picture under a really high-powered magnifying glass, you'll see that when you go from one color to another, they kind of mesh together and kind of into a gradient, smooth gradient. That's analog. If I take this picture and I say, all right, I'm gonna put this in a newspaper or a magazine. So here's the picture. I make a copy of it so I can put it in a newspaper. This is actually going to be a digital copy because this person now, when you look at it, is like this. The house is like this. Now, I don't know how much time you got because you're always in front of a screen. I don't know how much time you spend looking at a newspaper, but if you get a newspaper, the comics, the comic book section, the funnies, and you look at it under a magnifying glass, you'll see that what looks like a line is really a bunch of dots. Those are pixels. And the idea is that if I put enough of those dots in there, I don't know in the camera if you can see that, but if I put 2 dots there, you can see that. If I put more dots in there, you can still see that they're dots. But I can put so many dots in there that if I stand far enough away from it, it looks like a line, even though they're pixels. And the idea, when I said I'm throwing information away, is that good or bad? I don't know. I mean, if that looks like a line, if we're talking a picture, not audio, but a picture, if that looks like a line to you, you can't tell it's made of individual dots, and that's good enough. If not, you sample this at a higher resolution, and you put more dots in there, and it'll begin to look like a line. The point is that each one of these pixels, if it's a picture, it's pixels. If it's a graph, it's these dots here. No matter what, each one of these little positions here is represented by a binary number, these zeros and ones. Everything is given a numeric value. Now, why would we want to do that? I mean, what's the point of that? It seems like a lot of work. And it seems like if I'm throwing information away, that this signal wouldn't be as good as the analog. Well, it turns out there's a lot of reasons why we want to do this. One reason is if I want to do anything with this signal in a computer, you can't put in analog information in a computer. It's got to be zeros or one. All a computer is, and this is going to blow your mind, it's just switches that are either on or off. They're microscopic switches called transistors. Trillions of them that are either on or off that make your cell phone, any digital run. And a switch can only be open or closed. So we represent it in one state or another, and that's the purpose of digital electronics. So I want to talk about why would we want to do this? What's the point of this? Other than getting the signal into a computer, why would I want to digitize anything? Well, there's something called the digital advantage. And I'll ask you about this on the quiz or exam or something. But again, I don't know, since you guys are at home, you can just look it up, I guess. I don't know. This remote stuff, it makes it hard for me to test you like I want to because everything's right there. But I'll figure something out. The digital advantage. Okay, so before digital came along, everything was analog. And again, when I go back when I was a little boy, we had something called a cassette tape. Now, some of you, I can't see your faces. I'll say you know what a cassette tape is, and somebody in the class, people shaking their head, yeah, I know what a cassette tape is. But basically, it's a piece of plastic with rust on it. And we would actually record sound or music on it. Magnetically, you can magnetically store information on any kind of tape. That's analog information. And so back in the day when a new song came out, they had a record store. You guys download everything. We actually had to go up to the record store, and you buy vinyl or you buy a cassette tape. I would get the cassette tapes, and I have a cassette tape. I can put in my cassette tape player and I can play it. Well, let's say that you got a buddy and they listen to your cassette tape of whatever you do, and they say, hey, let me make a copy of that. Back in the day, we say dub it. Hey, man, let me dub your tape. He said, all right, I'll give it to you. You take the tape, and he would make a copy of it. So here's the original tape. I'm going to call that the master. That's the one I bought from the record store. So my buddy's going to make a copy. So this is copy 1. His buddy listens to the tape and say, hey, let me make a copy of it. Not of that, not of mine, but of his, because I don't know his buddy. So his buddy's going to make a copy of it. So this is copy number 2. And his buddy's going to ask for a copy of it. See where I'm going. If you keep making a copy of a copy of a copy, each one of these is a generation away from the master. If you keep making a copy of a copy of a copy, when you get 10, 20 generations down, 10, 20 copies down, the sound quality is going to sound like, well, this is going on YouTube, so I can't say it, but it's a four-letter word, begins with an S and ends with a T. It's not going to sound very good. One disadvantage of analog is it degrades. If you make a copy of an analog signal, the copy is never as good as the original. Now, if you make an actual physical copy on a copier, you can adjust the contrast to give you a better picture. But what I'm saying is, if you make no adjustments and you keep making a copy of a copy of a copy of anything, if it's analog, it's going to degrade. And eventually, you'll get so many generations away from the original, it's distorted, you got issues with it. That doesn't happen with digital. Why not? Well, the reason is, all these points here, which represent information, is stored as a digital number of code. So when I want to redo it, it'll give me, there's no way to get the 0 or 1 wrong. If the zeros and ones don't degrade, whatever this code is what it is. I mean, how many times you reproduce it. So digital quantities don't degrade. If this is digital, the nth generation, the millionth copy, is going to sound pretty much exactly like the master. Part of digital advantage is digital does not degrade. That's part one of it. The second part of it, I'm saying 1 and 2, but really there's many advantages that digital has over analog. I'm giving you the 2 that apply to this class. So digital advantage number 1, digital quantities, since they're represented numerically, they don't degrade. However many times you reproduce it, you just give that same code over again, and you got the exact code that was in the master. Digital quantities do not degrade. The other part of the digital advantage, and I don't really know how to show it to you, is you can compress the information. And what does that mean? You can take a lot of information and put it in a small space. You can only do that with digital. Well, that's not really true. You can compress analog a little bit, but nothing like you can with digital. I don't know. Some of you guys might not even be born in 1996, but in 1996 I got my first computer. No, it was 90. In 1998 I got my first computer. I graduated from college in 96. I graduated from college. In 98 I got my first computer after I got out of college with one of my degrees, and it was called a Gateway. That was a Cadillac of computers back in the day. My Gateway computer, you couldn't tell me nothing. I had a Gateway. I had a 500 megabyte hard drive. That was the biggest hard drive around. I was just like Superman. Look at your thumb drive. If you have a thumb drive, look at it. If you have a thumb drive, think about the thumb drive. If you ever took a thumb drive apart, I had to take it apart to see what was inside. The thumb drive looks like this. You got the part that you know, the handle, and then you got this part right here. That right there goes into the USB. That's the little plug thing that goes into the USB. Well, if you pry that thing open and take it apart, what you will see is a circuit board this is not drawn to scale, but I'm trying to emphasize something here. That the circuit board might be this big. There's different things on the circuit board, but somewhere on that circuit board is a little tiny chip like this. And that's where you're storing those zeros and ones. Whatever you take a picture of, when you make a video, when you take a picture, when you make a sound, anything that goes into your cell phone, your PC, any computer, anything that contains a microprocessor. Remember, microprocessors can only understand ones and zeros. So any information that's analog that goes in has got to be digitized, change the zeros and ones, and stored. Now, the point I was trying to get at is in 1998, when I bought that computer, my hard drive was a 500 megabyte hard drive, the biggest thing around. Your thumb drive is probably gigs. How many gigs is it? You can take my hard drive and put it on that little dot right there 100 times, 1,000 times. Part of the reason you can do that is because we can compress digital information. We can really compress digital information. So I want to emphasize that, the digital advantage. Advantage number 1, digital does not degrade. Advantage number 2, I can take a lot of information. You can see the higher the resolution. If I put more dots here, then I'm going to need more codes to represent those values. So I got to have more. I got to be able to store more information. It's a trade-off. The higher my resolution, the better the picture going to look, the better the sound, the better the video, the better the whatever. But the trade-off is that I got to have more. Trade-off number one is going to take more zeros and ones. So I got to have more storage. Those zeros and ones don't just sit there. Those zeros and ones, you got to move them around. That's another topic we'll talk about together. So if I have something at high resolution, when I want to move those bits from one place to another, either in here or over the internet or wherever, it's going to take a longer time to do it if I have a high resolution. So that digital advantage is pretty important. Now still got about 9 minutes. So I want to go a little bit deeper into this idea of digital. Make sure you understand what I mean by digitizing though. This is not a digital signal. You say either I have a dot or a no dot. No, digital, when you digitize something, remember it's a process. The actual digital is this stuff over here, the zeros and ones. It's a process to get to that. How did we get there? Well, we went here, we took the analog signal, and we sampled it. And then each one of those samples, we represented with zeros and ones, and we can store those zeros and ones, each zero or one, or I should say each code represents information. If I need more information, I increase the resolution. I got more codes. I got to have more digits to represent it. It's going to take longer to move around, and there's disadvantages to that. It's a trade-off. Now, let's talk about binary a little bit more, and then I'll let you guys go. And by the way, hopefully this thing is recording. I think it is. I don't know what happened last time. I felt bad because we didn't have the lecture, so I recorded it, and I was down here it was a nice lecture too. I was really proud of myself because I didn't know how well I would do with no students listening to me. So, but I just act like the camera was a person and I talked to the camera. But anyway, it didn't record. So hopefully this is recording and you guys can go back and you can look at it. Somebody told me to check out WebEx, and I actually did that, and I was kind of pissed off because I like to handle my own video because I like to put it up on YouTube. And WebEx, they force you to store information on servers, and I don't know if you have access to the videos, if I can download those or not. So I got to look at that a little bit more. But let me say this, and then I'll let you guys go. Once you have a value stored as zeros or ones, let's say you have one of these dots, a pixel, or whatever it is, a sample or something. And you're going to store that in binary. So maybe the code I use is 11010001 to store whatever that is. It could be sound, a piece of light, whatever you're digitizing. I store that. This is an abstraction. You're really not sending zeros and ones around, but that's silly to think about that. Because electrical devices only understand two things, voltage and current. Electrical devices only understand voltage or current. It doesn't even know what a 0 and 1 is. So what happens is in digital is what we call two-state electronics. Two-state. Now what does that mean? Well, in analog, your analog value can be anything. You can go from 1 volt to 1,000,000 volts continuously, or even you can have a negative voltage, a smooth, continuous change in some kind of signal. But in digital is two-state electronics, which means you have either one value or another. It doesn't matter what value it is. You might have 5 volts and 7 volts. And you might say, all right, you might have, let's say, 10 volts and 6 volts. You might say, all right, if I got 10 volts, that's going to represent a 1. If I got 6 volts, that's going to represent a 0. You got to have just two different values, any value. Now, in this class, what we're going to use, it's customary to use five volts to represent a 1 and 0 volts to represent a 0. Now, these are ideal values, and I'll I won't have time to do it today because I only got a few minutes. I'll tell you what I mean. There's actually the ideal, which we'll work with in this class, but I want to show you what we actually deal with in reality. But the point I'm making is that these zeros and ones mean absolutely nothing to your cell phone or computer or anything. It doesn't understand that. It only understands the presence or absence of a voltage or one voltage level and another voltage level. In other words, if I'm using this, there might be some kind of device like a capacitor. You guys know a capacitor holds charge. If you had me for circuits, we talked about that. Maybe I have a capacitor here, little microscopic capacitors. And each one of these represents a binary number. And maybe I charge this capacitor up to 5 volts. This capacitor is charged up to 5 volts. That's a 0, so that doesn't have a voltage on it at all. It's 0 volts. This is 5 volts. This is 0 volts, and that's 0 volts. That's how it's done. Now, they actually use capacitors, and they use devices too that are a little bit more high tech, but we won't go into that. But I just want you to understand that on the machine level, really what you're dealing with is the presence or absence of a voltage. In our class, this will be 5 volts and 0 volts. So a 1, when I digitize this information, this light, this sound, whatever it is really, I got 5 volts there on this whatever that's holding the voltage, the capacitor. A 0, there's no voltage in that capacitor. And if by doing that, putting a bunch of these little microscopic capacitors together, I can get this to store this binary number here. If I want to change it, maybe I charge these up and I can make it all ones. So the process of digitizing is just that. It's a process. I got about 3 minutes. So the main thing here to remember, I think in the beginning of the video when we start talking, we talked about the ladder. That's really important because this whole course is about ladder diagrams. The difference is we won't wire up relays and switches. We're going to do all that in software. That's what the PLC is done for. So it's taking all that control circuitry, all that logic, and replaced it with software. So that's important. So make sure you review that. But the big thing about this lecture is the difference between analog and digital. Basically, analog is continuous, digital is discrete. It's in pieces. You can say that. If I ask that on a quiz, analog is continuous, digital is discrete. But just understand that when you digitize something, number one, it's a process because you got to sample, you got to give that sample a binary number, and then you got to store those binary numbers. So you got to imagine, like this video you guys are watching, the speed at which this is happening. It's amazing because the lights coming in, that's analog. The camera's analog. Going down my USB cable is analog. Into the computer's analog. But then it's going to hit up to a circuit. We'll talk about this circuitry. A circuit called an analog to digital converter. So all this analog information going into this camera, my voice, the video, is being converted to zeros and ones. Really, the presence or absence of a voltage. So it's pretty amazing the way this stuff works. But anyway, I'm out of time. So hopefully this worked out. I got 2 minutes. I think what I'm going to do, the reason I wanted to go to Zoom, I've been using Blackboard all summer. Never had a problem out of it until the other day we tried to meet. I don't know what was up with it. The reason I wanted to go to Zoom is in this class, there are PowerPoints I have to share with you guys. I hate teaching from PowerPoints, but there's no other way to do this stuff. The whole class is not PowerPoint, but when I talk about the PLC, it's PowerPoints. So I was gonna, I could share the PowerPoints with you through Zoom. Well, I can actually do it through Blackboard, but it doesn't work very well. There's a delay. And so I figured Zoom, since it was a dedicated system, I thought it would work better, but I'm not sure that it will. So I think what I'm gonna do is this, is that when I need to have you guys here live, I'll let you know, hey, we're going to have a video link up, listen to the video. That way you can ask questions. You guys can open your mouth. Feel free to interrupt me at any time and ask questions. When I get to those PowerPoints, I don't know if you just want to sit here and have me listen, talk about a PowerPoint. I'm probably going to try to figure out a way to record those PowerPoints. And during those times, you don't even have to, you can listen to that anytime. We don't have to meet at a specific time. Well, that's going to start next week because we start posting those PowerPoints up. So I'm going to make the video, the lecture we had today, I'm going to record that and post it, and that way on Monday we'll be back on schedule. And our quiz schedule was screwed up. I was supposed to give you a quiz, but since the lecture didn't have it, I'm gonna send you something out over the internet. There's some kind of little assignment that's going to count a quiz. I want you to have a quiz grade every week, so I got to give you something. Does anybody have any questions for me? I see some people signing off, but any you guys have any questions before we dismiss? It's 2 o'clock now, so.
I had a kind of specific question about the binary storage.
Yeah, go ahead.
I know this might be skipping ahead, but notice there are different lengths of ones and zeros. Are those links dependent on the circuitry itself, or are there some devices that can have different links?
Oh, that's a good question. Beautiful question. So there's actually defined links. Now you guys can, matter of fact, I'm going to keep the camera going. You guys can pass it over. But if you want to listen, you can listen to this. I'm going to talk about this a little bit. This will also be on YouTube. I'll send the link out later. So there are predefined lengths. Let me talk about that. This will just take a second. Now I'm talking about binary in general, but you asked a good question because you connected that to circuitry, which you are skipping ahead, but that's okay. I like that. That shows me you're thinking. If I have just one of these right here, that's a bit. That's a bit. That can be a 0 or 1. Well, what you have is you can't really represent anything with a 0 or 1. You can say a light is on or off. If it's on, it's a 1. If it's off, it's a 0. That's all you can do. With 1 bit, you can't really do very much. Well, I shouldn't say that because PLCs are bit oriented. Most microprocessors don't work just with a single bit. They work with groups of bits. So the standard group, the standard bit size, if you will, I have 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So when you have these 8, the eight together is called a byte. A byte. So now I can start to represent information here. I mean, even when I was digitizing, if you think about it, when I was digitizing that signal, with 1 bit, I can't really represent much. With 2 of them, I can represent 4 pieces of information. With 3 of them, it's 2 to the third. There's some equation. I don't remember what it is, but you know that the more bits I have, the more information you can represent. So I'm working with a machine, a device. Most devices, with the exception of the PLC, are byte oriented, and that's not really true. But if I had a machine, this machine over here, machine A, and this is machine B, and if I'm working with bytes, now there's a couple ways I can do this. Let's say I want to send information out. It's going to send it a byte at a time. So it's going to send it this one, then this one, then this one, or it can start at the other end. I can have one line that does that. You can imagine that's going to be pretty slow. A better way to do it would be for each one of these to have a line. So I would have 8 lines from one to the other. And this is actually done in reality. I have 8 of these wires. So the byte is a predefined number of bits. Now, to be honest with you, most digital devices, no digital device, a byte used to be big. Now the byte is nothing. It's small. It's useless by itself. When you type the letter A on your keyboard, on your computer or cell phone or whatever, I don't know if you've ever heard of it. It's something called ASCII code. You can look that up. We'll talk about that. But every letter on the keyboard, upper and lowercase, every symbol, like the parenthesis, the exclamation, any symbol on the keyboard is represented. There's a fixed code of 8 bits that represents that. So a to U looks like that. But it's going to be 0, 1, 1. It's going to be some kind of value right here. So your computer is in a sense, it's byte oriented, but that's not really true because what happens is you got a bit, you got a byte, but actually you have something called a word. It gets a little confusing after this, but the point I was trying to make with you is the smallest chunk of information you can handle is a byte. Other than a PLC, any digital device is going to deal with bytes, 8 bits. That's just a standard. It's a world standard. But when we move information around, it would take a long time if I move 1 byte at a time. I mean, a kilobyte, kilo means 1,000. So imagine that. Imagine the size of your hard drive. And they talk about the number of megabytes or terabytes. Those are huge numbers. It would take forever if I did it, in a chunk of just 8 bits. So the word size it's machine dependent. And what I mean by that is, if you buy a Dell computer, it might have a 32-bit word. If you buy a HP, it might have a 64-bit word. So and that does determine the physical construction of the electronics. If I have a 16-bit word, I got 16 lines or 16 connections. If I have a 64-bit word, it's gonna affect the design of the circuitry. But the point I was making about the word is machine dependent. This is predefined. A byte is always 8 bits, but a word depends on who's the designer. You can have a 16-bit word. You can have an 8-bit word. You can have a 64-bit word. So it's machine dependent. For us in our class, a word is going to be 16 bits. So you'll see when you get your simulation software, there's going to be 16 buttons. There's going to be 16 of everything. You're going to wonder, well, why is it 16? Well, 16 because for us, a word is 2 bytes or 16 bits. So the actual physical construction of the PLC is affected by that. You're going to have 16 rows of switches. That's an excellent question. Who was that, by the way? Are you still there?
Tyler. Yeah.
Okay, Tyler. Yeah. Did I answer your question?
Yes, you did. That clears a lot of things up. Thank you.
That's a good question. That excited me for some reason. Anybody else have a question? Okay, I'm looking at the computer and people are disappearing. Your silhouettes are disappearing, so I guess you don't. I'm going to put this on YouTube. You can rewatch this later. If you do find that you have a question, please text me or you can email me, but text will be better. And if we need to hook up this camera thing and if it's something I need to go over again, I'll be happy to do that. We'll just set aside a time. You guys stay safe. Have a great rest of the day. And I'll see you guys on Monday. Don't forget I'm going to record the lecture I would have done today, and you'll have that information. Look at it over the weekend. See you later.
Thank you. See you.
Thank you.
Thank you.